How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our very special business today is a very important subject, which is commonly referred to as centrifugal force. Centrifugal force. And I'm going to put the word centrifugal in quotation marks because it is so badly, falsely, erroneously, incessantly badly used. Illustration. Here I have a ball on a string, and I whirl it in a vertical circle. If now at the top of the path, let us say, or at the bottom of the path, I let it go, I cut the string, does the ball go radially outward from the circle? No, it does not. It goes tangent to the circle at the place in question, like that. I'll show you that letting it go at the top. So, I point out by this argument that there is no force radially outward on the ball, a notion which is often badly used. Now, as an illustration of what I mean, here I have a little chamber in circular trough, tube, in which reside two spheres, and they lie at the bottom here. Question, I want to get one up that end, and I want to get the other up that end simultaneously. How do I do it? Obviously spin it about a central vertical axis, and there they go. Now it is commonly said that centrifugal force drove them out. But since this is not intended to be a lesson in physics, I can only say that that argument, that notion is quite wrong, as we will see in subsequent demonstrations. There is indeed a little toy connected with this, and I would have you see it, because it's quite enchanting for beginners to learn about the forces involved here. Here is a little circular trough, a toy indeed, in which reside two spheres, as in the bigger apparatus I used, and you will see that they lie one on each side of a partition. Question, I want to get one into a recess on one end of the tube and the other into a recess on the other end of the tube simultaneously. Solution, and when you play with your classmates with this, if one doesn't know it, you can always turn your back and surreptitiously, sort of secretly, spin it. I'm having a little trouble, but that is the way nature. There I have it, and each resides in its own little chamber at the ends of the trough. Now, I showed you in this demonstration that the spheres went outward. I now want to do a very classic thing which raises an interesting paradox. I have here another rotating mechanism. On this end there is a candle which I'm going to light, and I put a little chimney around it to protect the candle, and on this end there is another candle which I'm going to light, and I put a chimney around it to protect it. And now I am going to rotate this system about a central axis. And the question to be asked is, what do the candle flames do? Well, there are many possible things the candle flames could do. They could lean out, they could lag behind, they could lean in, they could lean out and back, which is sort of diagonally. They could do many things. But the reason I call this my candle paradox is that they do what is least expected. Watch, and we shall see them lean in. Watch it. They are leaning in. They are leaning in, which is an amazing thing. Regarding this fictional centrifugal force, supposing we had some water in this bucket. You know, one of the classics of all time, you can swing the bucket in a vertical circle and the water will not come out. Question, in the case of the ball on the string, whatever I did with that, oh, it's gone. If I swung the ball too slowly in a vertical circle, is it not true that at the top of the path, here I have it, and I'm going to show you, is it not true that if I am not going fast enough, the ball won't make the circle, it'll fall down? Question, supposing I have some water in this bucket, and I do this with it, and I don't go fast enough at the top, will the water fall out of the bucket? Nearly everybody says yes, but that's not true. Answer why. When the bucket is up here and the water is starting to fall down, the bucket falls down at the same rate, so the water does not come out of the bucket. So you see, this is an old fable, very falsely treated. Consider some more of the same. I have here two vertical steel hoops, which are fixed on the bottom, but free to move on the top of the central shaft, and I'm going to put these into a rotator, which permits me to spin the thing fast about a vertical axis. And I want you to see what happens, and we could then very reasonably say this is why the Earth is flattened at the poles. Watch it. I'm going to speed up the rotational speed about the vertical axis. Now, the consequences of the Earth's rotation on its own axis, about 1,000 miles per hour at the equator, because doesn't a point on the equator go 24,000 miles, 25,000 miles around in 24 hours? There is much consequence to this. Persons weigh less at the equator than they do at the poles for two reasons, both of which I'll leave to you to explore. Consider another consequence of this high-speed rotation. Here is a thing called a governor. There is a sleeve here on a vertical shaft, and if I spin this system fast enough, you know what will happen. The spheres will move in this fashion. The sleeve will move up on the central shaft, and it could well intercept a valve here, which would shut off fuel to the motor, and that's why it is called a governor. Oh, notice I'm pretty nearly on dead center. There it is, there it is, there it is, there it is, a governor. Here is one that you can do, utilizing this fictitious force of centrifugal stuff. Here is a coat hanger, and here is a coin, a penny, the lowest coin of the kingdom, I guess, and I'm going to put that coin at rest on the bottom part of the hanger, and I'm going to swing this hanger with the coin on it in a vertical circle, and I say I can keep the coin there. Why? The coat hanger will exert a force on the coin just as the string exerted a force on the ball to keep it moving in a vertical circle. Watch it now. Somebody says, well, I hope it doesn't work, Professor, because, you know, well, if it doesn't work, then I've lost my professional dignity, but there must be a reason why it doesn't work if it doesn't. And remember, we don't ever say that the experiment failed. Watch it. Oh, it did go around 2 or 3 times and then flew off. Let us consider now another classic, which is really quite astonishing. Here is a glass tube through which a string passes. And I have named this demonstration the string in the glass tube. Notice the elegance of that. A string in a glass tube, I've named it the string in the glass tube. Now here on this end of the string is a little 10-gram weight, and here on this end of the string is a 100-gram weight. Now you know that 10 grams can't hold up 100. Of course not. 10 cannot hold up 100. But I'm going to do something to the little one and thus give birth to a strange force which will hold up the 100. Watch it. There we are. There we are. The 10 is holding up the 100. Indeed, I'm going to make it lift the 100. There it is. Oh, I'll do it again. There it is, lifting it. Now we must never say that there is a force radially outward on this thing pulling on the string. Oh, wait a minute. I said something wrong, and I'm glad I did, because it may lead some of you to catch me up on it. I said there is no force radially outward pulling on the string. Yes, yes, yes. There is a force which the string exerts on the body, and there is a force which the body exerts on the string, but there is no force radially outward on the body. So you see, ladies and gentlemen and boys and girls, in the heat of this argument, I could very well make an utterance which the good people will quickly detect. And I'm glad I detected it, so you will see that there are occasions when I say things that are not right. Consider another of this business called centrifugal force. Here is a flexible loop which happens to be of rubber. I sometimes use a chain. Very flexible. It hangs quite limp-like. Now what do? I put it on a circular disc, and I rotate that disc at very high speed on a rotator such as I had here. And then I trip off the chain or the loop. Now look what happens. There is the circular disc. Here's the chain around it. And I bring this up to a high speed. And I trip it off. Remember, the chain was a limp structure. And what does it do? It rolls away as a rigid, solid iron hoop, for reasons which I leave to you to explore. Now, since I am given to the physics of toys, I ask you to consider another interesting little thing concerned with rotational motion. Here is a little toy which can shoot a hoop. A hoop. I will not reveal any of the secrets, but there is a rubber band which can give rise to a torque to turn the hoop. And, well, notice, it was an accident, but that's all right. I'm going to shoot the hoop away. Question. You will see the hoop roll away, and then you will see the hoop roll back. Or have I said it correctly? Let me invite your attention to this enchanting little business. Watch it. There it is. Now I'm going to do it again because I like it. And if I like it, that's reason enough to do it. Watch it. There it is. There it is. And I want to know what is going on. So you see, boys and girls and ladies and gentlemen, another bit of my philosophy here, my instructional philosophy. It is not always to answer the questions, but to raise some interesting dilemmas. Why things are so. Why things are so. Now, let me see what else we have here. I am not a cowboy, but the question arises. How is it that a cowboy can make a lariat or a lasso, L-A-S-S-O, often mispronounced lasso? How can a cowboy make the thing go in a circle, in a ring? Well, there it is. Notice the circular shape it took up. And the question arises, why is it circular? Interesting. Dilemma. A jug of water. Do you see again, ladies and gentlemen, and boys and girls, again some more of my philosophy. I use often the most plebeian and humble and simple and trivial things to demonstrate these wonderful properties of nature. How can I most quickly empty this jug? Watch it. There it is. And I thank you for giving attention to our business. This is the quickest way for the water to come out of the jug.